NMR spectroscopy. This is nuclear magnetic resonance spectroscopy. Same technology used in MRIs, magnetic resonance imaging. They just don't use the N on the front because if they put the word nuclear on the front of an MRI, nobody go get one. But in this case, it has nothing to do with nuclear radiation, but all to do with probing the nucleus or nuclei of atoms. And in this case, it is also a form of spectroscopy, meaning light is involved. In this case, the part of the electromagnetic spectrum we're using is radio waves. Notice with like IR spectroscopy or UV-vis spectroscopy, it's obvious which part of the spectrum you're using just from the name. But in NMR, you should just remember that it's radio waves. It's definitely not obvious from the name. The basis of this is that nuclei, which have an odd number of protons or neutrons, have a spin. This is the same spin you saw when you filled in like electrons and orbital configurations, stuff like this. So when you fill in two electrons in an orbital, they get opposite spins, and when they have opposite spins, they cancel. And in this case, same kind of thing. Protons and neutrons also have this property called spin. And when they're all paired up, they cancel. But if you have an unpaired proton or neutron, which occurs when you have an odd number of protons or neutrons, that nucleus is going to have a net spin. And those are the things we can look at with NMR spectroscopy. And the two big ones we're going to look at in organic chemistry are proton NMR, H1 NMR here, and carbon-13 NMR. Now, almost 100% of naturally occurring hydrogen weighs 1, but only 1.1% of carbon naturally occurring weighs 13. And we'll see some differences in those types of spectrums as a result. The idea is that when something has a spin, there's a magnetic moment associated with that spin. And in an external magnetic field, we end up with two possible energy states. So with no external magnetic field, these magnetic moments associated with these nuclei that have spin can orient themselves in any one direction. So, but with an external magnetic field applied, and here B is the letter we use in physics for magnetic field, they can either align with the field, and that's the low energy alpha spin state, or they can align themselves against the field, and that's this high energy beta spin state. And now that there's two energy states in this external magnetic field, this difference in energy corresponds to the energy of radio waves. So, and you can convert from the alpha to the beta state by absorbing a radio wave of just the right energy, and you can go back from the beta state to the alpha state, and that's accompanied with the emission of a photon of just the right energy in the radio wave part of the spectrum again. Cool. How big of an energy difference you have will tell you something about the environment that particular nucleus is in. Use a bigger magnet, you also get a bigger difference in energy, and a smaller magnet, a smaller difference in energy, and we'll see how we kind of normalize and account for that based on different size magnets.